Imagine, for a moment, floating high above the Earth, suspended in a small basket beneath a vast hydrogen balloon. The year is 1912, and you are the Austrian physicist, Victor Hess. For years, scientists on the ground had been puzzled by a strange phenomenon, a persistent, low-level radiation that seemed to come from nowhere. They assumed it must be emanating from rocks in the Earth itself. But Hess had a bolder idea. What if, he wondered, this mysterious radiation was not coming from below, but from above? To test this theory, he embarked on a series of daring balloon ascents, carrying sensitive instruments called electroscopes to measure radiation levels at different altitudes. On a fateful flight during a near-total solar eclipse, Hess ascended to a breathtaking altitude of over 5 kilometers. He expected the radiation to decrease as he moved further away from the Earth, the supposed source. Instead, he observed the complete opposite. The further he rose, the stronger the radiation became. At his peak altitude, the levels were several times higher than at sea level. This astonishing discovery could only mean one thing. The Earth was being constantly bombarded by powerful, penetrating radiation from outer space. Hess had discovered what would later be named cosmic rays, a finding so profound, it would earn him the Nobel Prize in Physics and open a new window into the universe. This discovery was a turning point in our understanding of the cosmos. It revealed that space is not an empty, tranquil void, but a dynamic and energetic place, filled with invisible particles traveling at incredible speeds. These cosmic rays are messengers from the most violent and extreme events in the universe, carrying with them secrets about the life and death of stars, the power of black holes, and the very fabric of our galaxy. Hess's simple yet elegant experiment demonstrated that sometimes, to understand the universe, you have to rise above the familiar and venture into the unknown, armed with little more than curiosity and a clever instrument. The initial puzzle was solved, but it gave rise to an even greater one that would occupy scientists for more than a century. Where exactly did these cosmic rays come from? The radiation Hess detected was a clue, a whisper from distant, powerful objects scattered across the heavens. It was the start of a cosmic detective story, a quest to trace these particles back to their sources and uncover the mighty engines that accelerate them across the vastness of space. This journey of discovery, which began in a simple balloon, continues today with some of the most advanced scientific instruments ever built, all aimed at understanding these potent visitors from the stars. So, what are these cosmic rays that Victor Hess discovered? They are not rays of light, as their name might suggest. Instead, they are subatomic particles, mostly the nuclei of atoms, primarily protons, which are the hearts of hydrogen atoms, that have been stripped of their electrons and accelerated to nearly the speed of light. Imagine them as tiny, incredibly fast cannonballs, fired across the galaxy by immense cosmic accelerators. They travel for millions of years, zipping through the interstellar medium, carrying an astonishing amount of energy. A single one of the most energetic cosmic rays can have more kinetic energy than a cricket ball bowled at top speed, all packed into a particle far too small to see. The great difficulty in studying these particles is that they are charged. The space between stars is not empty, it is threaded with weak, tangled magnetic fields. As a cosmic ray, which carries a positive electric charge, travels through these fields, its path is bent and twisted. It's like trying to trace the path of a steel ball bearing as it rolls through a vast invisible maze of magnets. By the time a cosmic ray reaches Earth, its trajectory has been scrambled so completely that it no longer points back to its origin. We can detect its arrival, but we cannot simply look back along its path to see where it was born. This makes finding their sources an immense challenge. To overcome this, scientists look for a different kind of messenger, gamma rays. When high-energy cosmic rays collide with gas and dust clouds near their birthplace, they produce a shower of other particles, including incredibly high-energy photons of light called gamma rays. Unlike the charged cosmic rays, these gamma rays are not affected by magnetic fields. They travel in perfectly straight lines from the point of collision all the way to Earth. By detecting these gamma rays, we can pinpoint the locations where cosmic rays are being accelerated, effectively allowing us to see the crime scene even if the original culprit has long since fled in a random direction. This is where incredible new observatories come into play. One of the most important is the Large High-Altitude Air Shower Observatory, or LHAASO. Built high in the mountains of Sichuan, China, LHAASO is a vast array of detectors spread over a square kilometer. When a cosmic ray or a gamma ray strikes the upper atmosphere, it creates a cascade of secondary particles known as an air shower. LHAASO's detectors are designed to capture these showers in exquisite detail. By analyzing the pattern and energy of the particles that rain down, scientists can reconstruct the properties of the original particle, determining whether it was a cosmic ray or a gamma ray, and measuring its energy with unprecedented precision. The data gathered by LHAASO and similar experiments has led to one of the most exciting breakthroughs in modern astrophysics, the discovery of PeVatrons. The name itself tells you what they are. The EV stands for electron-volt, a unit of energy. A PeV is a peta-electron-volt, which is a quadrillion, a 1 followed by 15 zeros, electron-volts. A PeVatron, therefore, is a natural cosmic accelerator powerful enough to boost particles to these mind-boggling energies. For decades, scientists theorized that such accelerators must exist within our Milky Way galaxy to explain the highest energy cosmic rays we detect. But finding them proved to be incredibly difficult. They were the missing link in the cosmic ray story. The discovery of these PeVatrons is a monumental step forward. It confirms that our galaxy is home to objects capable of accelerating particles to energies far beyond anything we can achieve in our most powerful particle accelerators on Earth, like the Large Hadron Collider at CERN. By pinpointing the gamma rays coming from these sites, LHAASO has identified over a dozen PeVatrons scattered across the northern sky. This provides us with a list of suspects, the prime candidates for the universe's most powerful particle accelerators. Now, the detective work can truly begin as we study each of these sources to understand the exact mechanisms at play. Providing yet another mechanism for particle acceleration. The search for cosmic ray origins is a truly global endeavor. The incredible results from LHAASO, for instance, are the product of a massive international collaboration involving hundreds of scientists from China, Italy, Thailand, and many other nations. This teamwork is essential because the challenge is so immense. By combining data from different observatories across the globe, astronomers can build a more complete picture of the high-energy sky. With LHAASO surveying the northern hemisphere, and other observatories like the HESS array in Namibia covering the southern hemisphere, we are piecing together the first-ever all-sky map of the universe, as seen in ultra-high-energy gamma rays. This new map is revolutionizing our view of the Milky Way. When we look at the night sky with our eyes, we see a serene band of starlight. But when we look with gamma-ray telescopes, we see a galaxy that is violent, dynamic, and fizzing with energy. We can see the locations of the PeVatrons, glowing brightly as they churn out cosmic rays. One of the most significant sources identified is a region called Cygnus X3, a binary system containing a massive star and a compact object, likely a black hole or neutron star, that is one of the most powerful particle accelerators in our galaxy. These discoveries are like finding the power stations that keep the galaxy alight with high-energy particles. This research does more than just solve a century-old mystery. It fundamentally changes our perception of the galaxy we inhabit. We now understand that the space between stars is not empty, but is constantly being stirred and energized by these powerful cosmic rays. They play a crucial role in the galaxy's ecosystem, heating interstellar gas, influencing star formation, and seeding space with the elements necessary for life. Uncovering their origins is not just about finding powerful objects, it is about understanding the very engine that drives the evolution of the Milky Way, and by extension, the conditions that allowed for our own existence within it. Of course, these powerful particles are not entirely benign. Cosmic rays pose a significant radiation risk to astronauts on long-duration space missions, such as a future trip to Mars. Understanding their sources, energy, and distribution is vital for developing effective shielding and ensuring the safety of human space exploration. Yet, this inherent danger is part of what makes the study so exciting. We are exploring a fundamental force of nature, one that both shapes the galaxy and presents challenges to our own expansion into it. Thanks to the legacy of Victor Hess and the work of thousands of scientists today, the veil is lifting on the universe's powerhouses, and our place within this energetic cosmos is becoming clearer than ever before.